In question number 29, we have been given a 2 kg block, and assuming that g is 10 meters per second square, the weight of this block is going to be 20 newtons. And further, it has been mentioned that this block is pushed against the wall, so that's the wall, and for clarity I've also shown the floor over here. So the block is pushed against the wall by a force of 40 newtons, which I've called F1, and there is mention of another force in the problem. That force I'll call F2. F2 is a 15 Newton force, and it has two properties as mentioned in the question. Number one, the force is horizontal, and number two, the force seems to be, it's given to be parallel to the wall. And your ability or inability to visualize this particular 15 Newton force has a great deal to do with whether you are able to solve this question or you are not. So for example, several students might be tempted just to look at the criterion number one, the force is horizontal, and if you try to draw a horizontal force in the plane of the paper or of the computer screen, then you're going to get a rightward 50 Newton force, or you're going to get a leftward 50 Newton force. There are only two options, and you realize that none of these forces are parallel to the wall. You see, the wall is over here. In fact, they are perpendicular to the wall. So naturally these two options are out of question. We have to draw the force in some other way. On the other hand, those of you who just look at the second criterion, that the force should be parallel to the wall, you might assume wrongly that the force is either vertically downwards 50 newtons or vertically upwards, because these are the only two ways that you can draw a force which is parallel to the wall. Once again, I'll draw the wall is over here. Now these forces don't fulfill criterion number one. They are not horizontal, in fact they are vertical, so naturally we rule these forces out. You need a force of 50 newtons which is horizontal as well as parallel to the wall. It should fulfill both criteria, and you must use your power of imagination in this question. Think in 3 dimensions. You can draw a force in 3 dimensions which fulfills both of these criteria. In fact, you can draw two forces. Imagine that there is a force which is coming out of the plane of the computer screen like that. It's a 15 Newton force. Now it is horizontal, there is no doubt about that, and it is also parallel to the wall. The wall is like this. You can use your imagination. The 50 Newton force I have drawn is parallel to the wall. And of course the second possibility is this, going into the plane of the computer screen. This is the other force which fulfills both the above criteria. Now it so happens that both of these forces, they are equivalent. These two forces are equivalent to each other as far as this particular problem is concerned. So you can see that at a later stage. We will of course assume a certain direction of the force and we will proceed. So for example, we can arbitrarily choose this particular force as the 50 Newton force described in the problem, and we will now try to draw it in the FBD. So going back to the FBD, I just have to show a 50 Newton force. So yeah, this is an arrow going into the computer screen, and by the side of it I'll show the magnitude. It's a 50 Newton force like that. Right, so this is not yet the complete FBD of the block. There are some other forces acting on it, and we can figure out one of them pretty easily. It's clear that whatever happens to the block, it's never going to move in this direction or in this direction. It's impossible for the block to move either left or right in this particular diagram, which means that there must be a force which balances this 40 Newton force, and of course we know that that's the normal reaction exerted by the wall. So I'll just show that force over here. It's a rightward force, is the normal reaction, so I'll just give it a name N1, and I know that it must be of magnitude 40 Newton since it balances another 40 Newton force. So you can see that in the FBD we have now drawn 4 forces, and there is going to be a 5th force. In fact, the question is directly about this 5th force, is the force of friction which is exerted by the wall on the block. And if you see the question, it's basically asking you whether the block will move or not. So if there is some static friction required for the block to remain in equilibrium, the question is whether the static friction, whether the limiting friction between the wall and the block is greater than or equal to the required static friction, in which case of course the block will remain static. And on the other hand, if the required static frictional force required, that is to keep the block static, exceeds the maximum static frictional force which the wall can provide, then of course the block will move. In short, we must ask ourselves, is the frictional force capable of preventing the motion of the block? Is it able to do that, or isn't it able to do that? So the solution of course is to be obtained by a procedure that we have done before often. We assume that the block is static, we calculate the required static friction, and then we see which of these two inequalities is fulfilled, and depending on which one is fulfilled we can predict whether the block moves or not. Now I think it's better if we can draw the block in another view. So you have to imagine that there is an observer over here. So this is the observer. The observer is looking upon the system like that, so in that direction. So that's the observer, and what will he actually see? So just to get a physical feel of this particular view, I'll first draw the wall itself. Just imagine that the wall is painted with some sort of yellow paint, so he's going to see this sort of thing. This is the wall, and of course he can see the block. So I'll just draw the block like this. So that's the block, and let me put the forces acting on the block in this view. So there's the weight, it's a 20 Newton, so W is equal to 20 Newton. Now according to this particular observer, the 40 Newton force F1, this one, it goes into the plane of the computer screen. So this is F1, the value is 40 newtons, and the normal reaction N1, it comes out, so that's another force. I'll just place it somewhere within the boundary of the block. So that's coming out, so that's N1, which is 40 newtons. I'm not calculating the moments of these forces, so it's not necessary for me to place the force at precisely its line of action. As long as the direction of the force is okay, it doesn't matter. Now look at the 15 Newton force, this one. So just use your imagination, place yourself or imagine yourself in the place of the observer, and it's clear that the 15 Newton force is going to the right of the observer, in the rightward direction. So I have to draw the force. Let's say I draw it like this. So that's 15 Newton. I think I'll give it a name in this diagram. I'll call it F2. Here also I'll call it F2 is 15 newtons. Right. Now the forces which are trying to move the block along the wall are this F2 and W. So what I'll do, before even coming to the question of static friction, I will just write the resultant of these two. Now that's easy. They are mutually perpendicular forces, W and F2, and they are in the ratio 4:3. So the third, or rather the resultant, their resultant must be proportional to 5. So if you just calculate, it's going to be 25 newtons. I'll just show the force, 25 newtons. So it's somewhat in this direction. It's something like this. So remember, the magnitude is 25 newtons, and you know that this angle is going to be 37 degrees, and likewise this angle is going to be 53 degrees approximately. And we can name this force, it's the resultant of F2 and W. We'll give it a name. I'll call it R. R is equal to 25 newtons. Right, so now let's go and calculate what is the required static frictional force to keep the block static. So remember, we are making the assumption that the block is static. What are the forces acting? F1 is a push. It is a push towards the wall. You're trying to push the block into the wall. The wall is reacting with a normal reaction N1, 40 newtons. And there's another force R of 25 newtons, which is trying to move the block parallel to the wall. That is, it's trying to slide the block along the wall. And naturally, if the block is static, which we are assuming it to be, then all the forces must cancel. The resultant must be 0. And F1 and N1, they anyway cancel. So the remaining force, which is the static frictional force, must balance R. In other words, this is the hypothetical static frictional force Fs, and in order to balance R, it must be in the opposite direction. That's how we have shown it, and its value must be 25 newtons. So that's the required static frictional force. Now let's calculate what is the limiting frictional force. The limiting frictional force is the coefficient of friction multiplied by the normal reaction, and that's 0.5 multiplied by N1 is 40 newtons. So that turns out to be 20 newtons. And now you compare 20 newtons with the required static frictional force of 25 newtons, and you immediately realize that you require more static friction than you can possibly get. You can get up to 20 newtons and you require 25 newtons. So in other words, it is this condition which is fulfilled. The required static frictional force is greater than the limiting friction. Naturally, the block is going to move, and if it does slide, then the frictional force is now kinetic frictional force, which is mu k into N1. Now mu k and mu s are not given separately, so we are going to assume that mu k and mu s are both 0.5. So 0.5 into n1 is of course 40 newtons. So the kinetic frictional force which the block experiences during sliding is 20 newtons. So I'll just change the FBD a bit. F static over here becomes F kinetic. The value of the force is 20 newtons, and the force is of course going to be a bit smaller, so I'll just remove this part of the arrow. And the direction of the force of friction is such that it will be opposite to the relative sliding. So you can see that the block is actually going to slide. See, it starts from rest and you apply this force R on it, which the frictional force is not able to resist entirely, and naturally the block must slide in the direction of that 25 Newton force R, like that. So the block will slide in a direction which makes an angle of 53 degrees with the 50 Newton force in the direction shown by the dotted arrow. And the frictional force exerted by the wall on the block during this sliding process is kinetic friction of magnitude 20 newtons. Finally, you may wonder why I drew the FBD from the viewpoint of this particular observer when I already had drawn an FBD earlier, this FBD on the left. So the reason is this force R, which is needed in the solution, I cannot show it in the FBD on the left hand side. Just imagine it is the resultant of the 50 Newton force and the 20 Newton force. So if I try to draw the arrow itself is not in the computer screen, it's not in the plane of the screen, so it's not possible to draw that arrow in the left hand side FBD, and therefore I drew the FBD from another viewpoint. So this is sometimes required in questions. You have to draw the FBD from a particular observer's viewpoint, and then the question becomes easy to solve.